Now we're going to start with the most bare bones, and I want you to also realize that each time for each one of these slides, most of them anyway, you're going to see a different phrase up there. That's because proportional reasoning problems, they may not actually say, please use proportional reasoning to solve this problem. They'll give you a problem and then they'll ask something like, how does the final force compare to the new one? What is the ratio of the forces? How does it change? Okay? So I tried to put a couple of different ways of phrasing it in there so that we can do this. What we're going to look at is we're going to look at how to find the ratio, and we're going to do the forces that are acting on it. So here we go. So the force of gravitational force, I use big G to indicate we're talking universal gravitation. If you notice, the AP sheet doesn't specify, it just says G, little g. But anyway, I'm not going to use equal, I'm going to use proportional, m1, m2 over r squared. Why am I using proportional and not equals?
Because G is the constant.
I took the G out, right? Okay, so now then, so this is what our proportionality is, so I'm going to go ahead and solve for it. So the coefficient of the first mass is 1, the coefficient of the second mass is 1, and the coefficient of the radius is 1. And that'll be squared because it's squared. So that means the ratio of old to new, or whatever we want to say, is 1. So let's go ahead. We draw our forces. What is going to be true of all of your force diagrams, the force vectors? They all go towards the middle. There's two things then. What's the other one? They all go towards each other, and nope. They're all the same size because of Newton's third law. Doesn't necessarily mean they equal 1, but they are the same. Okay. Well, yeah, that's what you meant. Okay, so let's do this one. All right, let's do another one. Let's mess it up a bit. So on this one, we're going to go ahead and we're going to take the same masses, but now we're going to double the distance between them. So when we do that, what happens? How much does the force of gravity change by? That's a big G, like I said, keeping myself consistent. So the force of gravity is proportional to m1, m2 over r squared. The coefficient of the first mass is 1, coefficient of the second mass is 1, coefficient of the radius is now 2, and that'll be squared. Alright, so that means the force of gravity changes by a factor of 1/4. Now, using what the first one was as our basis, let me see this here. That means that my force arrow is going to be itty bitty on this one, isn't it? Itty bitty, because it's 1/4 of that first length. Does that make sense? Okay, we have a couple more examples in here. Next up. So now, from the first scenario, we're not going to double the distance, we're going to cut it in half. So what's our ratio of change? Set it up the same way. Force is proportional to m1, m2 over r squared. What I am showing you with this process is how you'd be answering it in a free response where you have to show why something is the way it is. Alright, so 1 is our coefficient of mass 1, 1 is our coefficient of mass 2, and now 1/2 is our coefficient of our radius, which means it's 1 over 1/4. And when you divide by a fraction, you multiply by the reciprocal. So the ratio of change then is 4, or you could say 4 times. So that means when I draw my vector, yep, it'll go pretty far out, and so will the other one. By the way, that r squared and the m thing, this is why black holes happen. At its most basic level. You get too much mass too close together, that force of gravity between them gets bigger, and it gets bigger fast. Okay?
Miss, I just something, but did you say black holes?
Holes with an H.
I heard holes.
Okay, no, it's okay. All right, moving on. Example 3. So now we are doubling both of the masses and we are doubling the distance between them. So we want to compare our new force of our final force of gravity, we'll say final instead, final force of gravity to the initial force of gravity. Force of gravity is proportional to our equation m1 m2 over r squared. In this case, our new coefficient of the mass is 2. New coefficient of the second mass is 2. And we are going to double the radius. So we end up with 4 over 4, which means 1. So in this case, if I'm going to compare these two things, I can say that there is no change, that the force of gravity final is equal to the force of gravity initial. All right, looking at this, what is the non-mathematical clue that it's going to be 1?
All the same number.
They all changed by the same factor. Each variable changed by the same factor. And when that happens, there is no overall change. So then that means the size of our forces is simply as big as the first one, because it's still, whoops, can I do this? Nope. Okay, so we doubled the mass, we doubled the distance, but we did not double the amount of force that each one is acting on the other. All right. Do another one. Actually, for the next one, give me a second.